Okay, here she comes. In the spotlight. So, good afternoon, ladies and gentlemen. For those of you who have seen this morning's session, they know me. I'm Josh Hamsch. I'm the chairman of the first afternoon session. And I would like to welcome Katrien Kolenberg from Belgium. She's a professor at the universities of Leuven, Antwerp and Brussels. So she has to subdivide herself into 3 cities. Luckily, Belgium is not that big, but it has a lot of traffic between the cities anyway. So her talk will be on Lyrae stars, cosmic lighthouses with a twist. Please.
Thank you very much, Josh. That is okay. Great. Thank you. Good afternoon. Thank you for the introduction, and a big thank you also for inviting me. It's a great honor and pleasure to be here, precisely because, as Josh pointed out in his talk this morning, Pro-M collaborations mean a lot to our Lyrae studies, and that's something that I also want to illustrate in my talk. Although I will also talk about the things that that we are doing from the modeling side, etc. But actually, to feed these models, we need data over long time scales, and this is something that has been historically provided also by people who are not only professionals. And people in this room who are professional amateurs are really contributing to that. So what will I talk about? First of all, we know our Lyrae stars are useful as variables, so I'll talk a bit about what are they, for those who might not be familiar with it. Then I'll talk about some unsolved riddles. One of them is the famous Tseraskaya-Blaschko effect, known better to you probably as the Blaschko effect, but I'll go into that. And also, what are the models that have been proposed historically for that, and where are we today on this riddle that's up to now unsolved. Then Robert this morning already talked about the revolution that space photometry has brought for astrophysics in general, and this has also been the case for our Lyrae stars. So as I bring my story on the Blaschko effect, I'll bring in also what space photometry has brought and how this has led us to new possible interpretations of things we don't understand yet. So we'll see these old friends, the Lyrae stars, in a new light thanks to these new data. But actually that leads to more unsolved riddles, as usually is the case. And that's why I'll end with other parts of exploration, and actually people in this room can play an important role in this, both for photometry as for spectroscopy. Okay, let's dive in. We know that our Lyrae stars are what we call pulsating variables, so what's happening to them is something that is intrinsic to the stellar structure inside. Something causes them to pulsate, to vary in brightness. And we humans, we like to put things in boxes, so we have put these Lyrae stars in a specific box, and that's what we will focus on now. Now, how have they been found? They were first discovered in the end of the 19th century, beginning of the 20th century, as stars that really importantly change in brightness, and they were seen mostly in globular clusters. That's why initially they were called cluster variables, and the man you see on the left here is Solon Bailey, and he was one of the people who initiated a survey of the sky looking for transients, for things that changed, and they also observed, of course, a lot of these are Lyrae stars, many of them in globular clusters. Here you see how this light varies. Now, at the time, we didn't get such precise light curves yet, but what was found was that these have periods of typically days, and in this animation, you can see them blinking, globular cluster M3. This is an animated movie made by Zoltan Kolat, who, just like me, is also very interested in the actual sounds that are linked to the pulsations of these stars. And you see that it's very easy to pick up an Lyrae star. And you also see that there's many in this globular cluster. Globular clusters are typically very old objects, at least 10 to 12 giga-years, so billion years. And that's where we find these stars. They are old stars, retired stars. And that brings me to the general properties and also why they are useful. So these stars, they are almost about the same brightness. That means that if you see them further away, they will appear less bright and vice versa. So we can use them as standard candles. Also, I just mentioned, you can find them in clusters, old objects. They have been around for a long time. They are not main sequence stars anymore. They've lived a long time, and they therefore are witnesses of the universe and the evolution of our own galaxy and other galaxies at a young age from the start. And then finally, they have been for a long time considered to be prototypes of purely radially pulsating stars, which means that, as the star vibrates, it expands and contracts, and it stays a ball, it stays spherical, and I'll illustrate that a bit more. So this fact that they are standard candles, just like the Cepheids, means that they occupy within the distance scale ladder, they occupy a specific step there, and the thing is that they are actually, they have large variations. They're not as bright intrinsically as Cepheids, but they're much more numerous because they are less massive, so they come more frequently, they occur more frequently, and we can actually now see them up to other galaxies, and so that's why they're useful. They are found in globular clusters. They're found in different parts of our galaxy, not only in the clusters. Later, they were also discovered in the field, in the disk of the galaxy. And the name RR Lyrae is just the name of the brightest star of this class that was discovered in the field. You find them in different parts of the galaxy, both in the disk, in the halo, and also in the outer halo. And that's also why they're useful. So we can use them for galactic archaeology to see how our galaxy and other galaxies have formed and evolved. Because even between our galaxy and then the Andromeda galaxy, which is located at 2.5 million light years, in between we have found recently RR Lyrae stars. And so because we can use them as distance indicators, that we can estimate their distances. We know how far away they are, but we see them right in between. So we see that these galaxies are actually much bigger, as the light just tells us. They are part of what we call this circumgalactic environment, where we find dust and gas and also RR Lyrae stars. So they are very useful tracers of the structure of our galaxy. We can use them for distances, and moreover, they pulsate, and pulsations are useful to tell us something about stellar structure. So what you see here is a drawing of what Solon Bailey, this man who initiated the first surveys that found RR Lyraes, made. And he saw that some of these RR Lyraes have large amplitudes, others have smaller amplitudes, and he subdivided them into A, B, and C types. In the end, later we understood that these A and B types, they're actually manifestations of the same thing happening in the star, namely the star contracts and expands, and for the A-B types, we have what we call the radial fundamental mode, which means that all the layers of the star are expanding and then contracting again, maybe not all at the same speed, but grosso modo, the whole star expands and contracts, or at least the layers that have the freedom to move a lot. Then you have the stars that pulsate in the first overtone. These are stars that have in between the center and the surface of a star a nodal surface, and above and below that nodal surface you have the radial motions. So this is a schematic representation. You can even go further, so you could speak of the second overtone, etc. These second overtone RR Lyrae stars are extremely rare, but these are very common. And the fundamental modes are the RRAB stars. These are pulsating with higher amplitudes. And the RRC stars that have slightly lower amplitudes of about half a magnitude in the visible, they are the ones pulsating in the first overtone. And because, of course, the star is making different motions at the same time, they will not attain the same high amplitudes as the RRAB stars. So that is the simple physics that's behind. That is that the star is vibrating in this simple mode. Yet we see stars that are doing a bit more complex stuff, like this one, measured by 2 Hungarian colleagues. And you see that here the light curve is not as repetitive as we saw before, but you see a combination. And this is a combination of both the fundamental mode and the first overtone. Now, what stellar models teach us is that, a star, a sphere of gas, can become unstable. When it becomes unstable, it starts to vibrate. It can vibrate in one mode or usually multiple modes. And for these radial modes, for our Lyrae stars, you have a specific ratio between the frequencies that is typical for these RRC stars, typically RRD stars, excuse me. So it's typically about 0.74. That's the ratio between the 2 periods. And it depends on the mass. But that's how we know that we are dealing with an RRD star that's pulsating in these 2 modes simultaneously. These stars are much more rare than the RRABs, which are the most common ones, and then the RRCs. And we're still figuring out what makes a star RRAB, RRC. RRABs are the ones that have the lower temperatures, RRCs have the higher temperatures. Maybe these are the ones that are in a transition between the 2. But of course, these are stars that are billions of years old, at least 10, 12 billion years old. It's very hard to catch them in their evolution. They might have this pulsation for millions of years without a lot of changes, yet since we know thousands of them, sometimes you see small changes on shorter timescales that might reveal a bit of evolution in these stars. And then we can learn about what exactly causes them to choose one kind of pulsation over the other. And that's what makes it interesting, because from these vibrations we want to get back to the stellar structure. Now, what causes them to vibrate? Here you see such a radial pulsation, and you see that not all layers are moving at the same speed necessarily. Usually the outer layers are lagging a bit behind, and they have a different speed. We can derive that also from spectra. We call this the Van Hove effect. But something is driving this. And what's driving this is that inside of the star, there are layers that can act as a motor, as a driver for this pulsation. And the mechanism behind this is the so-called kappa mechanism, where kappa stands for the absorption, basically the capacity of a layer in the star to absorb incoming radiation. And this kappa is, of course, you can have it for it, you can calculate it, you can model it for every layer. But what is typical in this kappa mechanism for pulsation is that when the kappa mechanism is active, that when you compress the star a little bit and you get the layer closer to the center, kappa goes up. The opacity increases. And what happens then is that the radiation that comes from the inside, that is also caused by the fusion inside, it will want to go through the layer, but the layer absorbs it, and it will start pushing the layer outward. So you'll get this radiation pressure that pushes the layer outward. And then when the layer goes out, goes to lower temperatures, the kappa goes down. And then what happens then is the radiation goes through, and the layer, due to gravity, it falls back. And it's basically because a star is an eternal battle between the pressure from inside and the gravity that wants to, from outside, that wants to compress the star. And in this case, the kappa mechanism causes that this is temporarily unstable, but with a very regular frequency. So the fact that with compression, this kappa goes up, supports the pulsation. Now, why does this kappa go up? It is because in certain layers in the star, because of the temperature of the layer, and the star is a mixture of gas, different elements, you get ionization depending on the temperature, and depending on the temperature, you might have more or less ionization. And we call these layers of partial ionization. And now when a layer is compressed, you might get more ionization, which makes the kappa go up, and vice versa. So this is why in these layers where the ionization is not complete, you will get driving through the kappa mechanism. And that's what happens in our Lyrae star. So it's the layers in which hydrogen and helium are partially ionized that can drive this pulsation. And this is what holds for our Lyrae stars, for Cepheids. In other types of pulsating stars, it might not be the hydrogen, it might be the metals. And then it would be at higher temperatures that they're partially ionized. But basically, is this kappa mechanism that will act when this layer in the star that can sometimes have a higher, sometimes a lower opacity, absorption capacity, is located at a good depth. And it has a specific temperature to have this property, and it has to be located at a good depth. If this layer is too deep in the star, actually the radiation will not be able, the pressure of the radiation from inside will not be able to push the layer very far that it's observable in the outside. If the layer is too far out also, then it will not have the effect that it can be maintained, this pulsation. So it has to be at an optimal depth in the star, and that's why we have in this Hertzsprung-Russell diagram, as you see here, so this is an HR diagram, you have this zone where you have the kappa mechanism at a specific location where you have a right combination of temperature and luminosity for these layers to be located at the right depth. And that's what we call the instability strip. And that's where these RR Lyrae stars are situated, but also the different types of Cepheids that are there, also Delta Scuti stars, even some of the white dwarfs that are pulsating. So all of these is caused by the same mechanism due to a variable opacity in layers in the star. Okay, so that's why they are doing it, and that's why, in the HR diagram, you see here the Hertzsprung-Russell diagram with pulsating stars, and that's why you see so many, especially in this zone. And here they are driven by the kappa mechanism for hydrogen and helium, and then for hotter stars, you will have this for metals. Okay, now these stars are our Lyrae stars. They have the right properties to be in this instability strip, and here you see their parameters. So this is, the periods are typically between 0.2 and 1.1 day. That gives them a specific absolute magnitude. Then they have a specific temperatures, specific log G values. So this is the gravity. Then here, this is the metallicity. You see that many of them will actually have very little metals because they are old objects. So they were formed earlier in the history of our universe. There were less metals around. But in the field, you will see some RR Lyrae stars that have metallicities comparable to the sun, but they're more rare. Then their masses, actually, we have never been able to measure like one normal RR Lyrae star's mass. And the reason is, is puzzling because we don't know that many RR Lyrae stars that are in a binary system for which we can derive masses in that way. So what we use are models. And masses are probably, it started from stars that were maybe up to the sun, but maybe 0.8 solar masses. And then in the course of their life, they might lose a bit of mass and they will end at 0.5 to 0.7 solar mass. So that's what we suppose from stellar evolution that will be the masses of the RR Lyrae stars. And then they are, they're less massive, but they're bigger than the sun. So on average, 5 solar radii. And during the pulsation, as they vibrate, they expand and contract, so they become bigger and smaller. And this will be with a variation of 10, 15 to 20% of the radius. So you can imagine it's quite spectacular if you live around an RR Lyrae star, because this happens every half a day or so. Okay, Now, radial pulsations, I talked about those. Of course, for our Lyrae stars, these are the simple ones, the ones that are fundamental or the first overtone, but you can go much further. And then I want to say a little bit about non-radial pulsations. What happens there? These are also vibrations that are possible. You see them in many other stars. And here, the spherical symmetry is broken. And the star basically starts changing its shape. It starts moving in different ways, and it's not a sphere anymore. And you can describe this mathematically using what we call the quantum numbers. So you can, any kind of movement of a sphere, you can decompose it in these kind of what we call pulsation modes. And it's perfectly describable mathematically. So here you see the different types of non-radial pulsations depending on how the star is changing shape, and you see that in the moving images below. We will say, okay, is it symmetric with respect to the rotation axis? If it is, we call it axisymmetric. If it's not, then it can be either tesseral or sectoral, and the sectoral modes are the ones that resemble like an orange or a mandarin. So these are, you can classify everything, and any kind of motion that the stellar surface makes, you could decompose it into a combination of these. And that's basically the key of what we do in astroseismology. We are trying to reconstruct from all the different frequencies that we see, all the different variations that we see, what is the star doing and how can we decompose it in these basic components. Now, why am I telling this for our Lyrae stars? Because I said before that they are typically radial pulsators. But the thing is that now that we have so many good telescopes, so much data, that we see other frequencies that we cannot explain as being just radial. So we think that there are also non-radial modes in our Lyrae stars, and then we'll have to identify them. And so that's what I've been trying to do in my PhD work, and what we can try to do also looking at all the frequencies that we see with, for example, Kepler, TESS, etc. So that's when we get to do astroseismology. Then the more modes, the merrier, basically, for astroseismologists. For our Lyrae stars and Cepheids, we've usually been spoiled with very simple modes that are radial, that are easily described. But once it gets non-radial, it gets more complex. Okay, well, I said before, our Lyrae stars, they are located in the HR diagram on the horizontal branch, so they are horizontal there. They all have about the same brightness, but they are in this period luminosity diagram. They are the ones that have the shorter periods with a less brightness, so you can use them for distance determinations quite close by. And then you have the Cepheids here, and we know that there's other types that expand this diagram. This relation was discovered by Henrietta Leavitt, and actually thanks to stars like our Lyrae stars and Cepheids, which have revealed such a clear relation between their periods and then their brightness, we know that the universe is much bigger than it is. So that's what made Hubble conclude in the end that the nebulae that they saw all around are actually far away and not part of our own system of stars. Okay. And then to end this part of the talk, well, our Lyrae stars, they have these radial pulsations, but if you have non-radial pulsations and you know to which depth they go in the star, that will help you also to reconstruct a lot of the different layers of the stars and to make a complete reconstruction, to do tomography of the star just based on the frequencies that you see in the star. And that's what we could try to do. So if we see a star vibrating with many, many frequencies, then we try to identify these frequencies and see how that would work with the stellar models. Now let's go back to the RR Lyrae stars. I said they were found in clusters, but in 1913, there was a paper that talked about the cluster variable RR Lyrae, and that is the one that was discovered by Williamina Fleming, who worked at the Harvard College Observatory and saw stars just like they saw in the globular clusters, but this one was much brighter and just in the field. From this paper, so Tucker published it based on the data taken by Williamina Fleming, and this is the light curve. It's folded now with a period of about 13.5 hours. And you see that, you see a clear variation of about 1 magnitude. You also see a lot of spread in the data. Now, about a century later, we also got data collaborating with different observers from all over the planet, all in the northern hemisphere. These were data from 7 observatories that were combined in a paper, and here you see the same star. And you see actually that the spread was seen by Williamina, that it's something that is inherent to the star, because what you see here, the red curve is the average light curve, and then the blue curve is the data binned per 4 days. And you see that as you go through the total cycle of about 40 days, that the light curve significantly changes shape and amplitude. And also that the time of the maximum changes. So the time of the maximum changes, that means that the period actually changes. It's the phase variation and the amplitude variation. So this effect that we see in our Lyrae was found already in 1907 by Blaschko. Actually, Blaschko reported on it, but it was found in that particular star by Tseraskaya. And here you see basically what it's about. So you have the radial pulsation period. Typically, it's half a day. And this is modulated over time scales of typically days to tens of days. Tens of days, months sometimes. The shortest ones are just a few days, but the longest ones are hundreds of days. So this is the very simplified picture of this modulation effect. And we see it both in amplitude and in phase, as we saw on the animated GIF before. And it turns out to be very common. Actually, it turns out that about half of the stars that are RREB stars, like RR Lyrae in the figure before, that have these higher amplitudes, that they are modulated. Half of the stars. That's a lot. Why half? Exactly, we still don't know. Now, with this Blaschko effect, I want to make a remark, because my friend and colleague Don Kurtz wrote a review on pulsations across the Hertzsprung-Russell diagram recently, and he did some research into the original publications. And he went back to this paper of Blaschko that we all cited, that was in Mitteilungen für ähnliche Sterne oder so, in a German paper, but it was of course translated from Russian. And Blaschko mentioned there that it was not him who found it, but it was Lydia Petrovna Tseraskaya who had found it. So this is why from now on we will propose to use the Tseraskaya-Blaschko effect. Just like we don't speak anymore of the Hubble law, but the Hubble-Lemaitre law, why not change this name? Okay. Tseraskaya actually has, she did a lot of work, and she also has a crater on the moon named after her. Now, how did they find it? Well, they used O-C diagrams. So they looked at what is the time of maximum, when do we observe it? Does that correspond to when we expect to see it? If it does, then this observed minus calculated value is 0, and you have a flat O-C diagram. But if the period is incorrect but constant, you will see a line. If it's changing, you will see not a straight line. Why would it change? It could be due to evolution. We see a lot of period changes in our Lyrae stars. Is it evolution? Is it something else? Not so clear. It could be that the star's period suddenly changes, and I think some of you have already observed this in some stars. So that's also puzzling. You have these abrupt changes, and maybe there's even binarity involved in these O minus C diagrams. So that's what we try to figure out, and this is a very useful tool to figure out what's happening in the star if you just have data, even if you just have times of maximum light. Now, for this Blaschko effect, there's a problem, and that is that it's not always as regular as it seems, as I presented in this figure. A lot of our Lyrae stars show changes in their periods on a time scale that is too short to be of evolutionary nature. Often also we see that the Blaschko effect doesn't show an exact repetition from one cycle to the next. Sometimes it does, sometimes it doesn't. And then also we see in some stars, like our Lyrae itself, longer cycles in this Blaschko effect. Our Lyrae, for example, has a longer cycle of about 4 years. So that's puzzling. We could also ask the question, does the Blaschko effect or the Tseraskaya-Blaschko effect occur in other stars? There have been several papers referring to the Blaschko effect for example, Cepheids or high-amplitude delta Scuti stars. The question is whether these mechanisms of modulation are the same or not. Also, this is not completely answered yet. But we do see amplitude and phase variability in other types of pulsating stars. And there, not rarely non-radial modes are thought to be the culprits, like for the delta Scuti stars, but more research is needed for this. So as far as this Blaschko effect is concerned, we are still a bit in the darkness, although there are some clear favorite models. But in the past century, several models have been proposed to explain the Blaschko effect. And when I entered the field, there were 2 models that were competing, the resonance model and the magnetic model. And I'll go a bit deeper into them. So there are papers that explain what is happening. On the left, what kind of modes could be resonant with this main pulsation mode of the Lyrae, or how could a magnetic field cause variations? And let me briefly explain that so that you see how we reason about this. So these 2 models were opposing each other. And then there's also other models that might involve only radial modes, and we'll go into them a bit later. But these resonance models, initially they thought that there would be a resonance between radial modes, but actually these radial modes, they are too far apart to give the frequencies that we see for the Blaschko effect. So they thought it was a resonance between the radial mode and then a non-radial mode. So the star actually doesn't remain spherical, but it changes shape a bit. And then you might have, because the frequencies are close enough, a resonance. And that would give rise to this modulation as we see it. And in that case, the prediction was that in the frequency spectrum, if you do a Fourier analysis, for example, and you look for the frequencies, you would see these signs of modulation, these equidistant peaks, which we do see. We see equidistant peaks, but is it specifically due to another mode there, or is it something else? Now, these were the models that looked into this. These were published models for this resonance model. And actually, this is a figure from one of these papers. And what this paper showed, they did calculations for different Lyrae models, and they found that in the vicinity of the frequency of the main modes, so the radial modes, you would see also the potential for non-radial modes to become unstable. And if they are close enough, they could go into resonance, and that could give rise to a modulation. So the models seem to say, okay, there are potentially non-radial modes in the star, but then the question was to find them. Now, on the other hand, there were models that also could predict such multiplets as we see in the frequency spectrum, but that are relying on a magnetic field. And in these models, you have a magnetic field in the Lyrae star, of which the axis, the magnetic axis, is inclined with respect to the rotation axis, which means that as the star rotates, we will get another view on this magnetic axis. Also, of course, we don't look exactly on this axis, so this is the line of sight. And this is where the magnetic field is oriented. It was supposed to be a dipole field. And then this dipole field would cause the main radial mode, so the spherically, symmetrically pulsating mode, to become a non-radial mode. So it would get what we call dipole components, and it would look like this. Quadrupole components, excuse me. So it would become deformed like this because of the magnetic field, this pulsation. Now, as the star, and so this is corresponding to a non-radial mode with L equal 2. Now, as the star rotates, our view upon the star changes, and we would get a different view upon this non-radial mode. Sometimes we would see more going out, sometimes we would see more going in, depending on the star's rotation and how we look at it. And that's how, in the end, we could also see brightness variations. Now, for these models to work, well, actually, on the one hand, these models predict also, because you have a non-radial mode of degree 2, they would predict in the frequency spectrum also these multiplets that we see, but then with 5 peaks in total, so 2 equidistant at each side. And the Blaschko frequency would then be actually linked to the rotation frequency, because it is because the star rotates that you get to see the star in a different way. So that's a thing that we could test also when we look at our Lyrae stars. And these were models that proposed it, sometimes even for other types of stars, this model. But yeah, this model had some problems, because for this model to work, and actually for the radial mode to be deformed so that you could see its deformation, you would need a large magnetic field. And the predictions were you would need at least 1 kilogauss. So that's a big field, so we could try and look at spectra and see if we see traces of a magnetic field there, looking for the Zeeman effect in the spectral lines. And then that's what different observers did, and what they saw was quite contradictory. So in '58, Babcock said, yes, clearly a magnetic field that is changing with the Blaschko phase. So that's something that you might expect to see. But then Preston tried again, and he saw nothing. And then Romanov saw something in 1994. Then Miriam Shadid tried again, and she saw nothing. You could also look at, since the Blaschko period has to be related to the rotation period, what rotation periods do these stars have? So you could also look at, can we derive this? You can derive a rotation period by looking at spectra, and actually, if you look at the broadening of the spectral lines, you could get an estimation of the rotation, and it turns out that what we see is not in contradiction with the Blaschko periods that we see. So it could be okay. But then, so these studies were done for our Lyrae itself, the brightest star, by far the brightest star, for which it's easier to get spectra, easier to get enough signal to noise to derive whether there's something there or not. But then in 2009, together with Stefano Bagnulo, we looked at a set of stars, different stars with Blaschko effect, without Blaschko effect, in the southern hemisphere. And we looked at, I think 17 stars, and we found no magnetic fields at all. So that's something. Then after that, we left this model aside, at least I did, because also it's not easy to find these magnetic fields. If they're smaller, it will be very complex to really find them. So these two models were standing for many years, but then in 2006, there was another model proposed by Stotters, a new explanation for the Blaschko effect in our Lyrae stars. And if you read the paper, he writes like there's been a lot of confusion, and actually the two models that are there, it's already a long time that they don't really match the observation. So let's come up with another model, and that is linked to the variable turbulent convection. And I'll talk a bit more about that when I come to the right slides. But what he actually summed up in his paper was also, there's a lot of things that these models don't explain, because if you look at these modulation components, they have unequal amplitudes. The models don't explain that very clearly. Also, the RRC stars, the first overtone stars, they are much less modulated than the RREB stars. Why would that be the case? Maybe they have less magnetic field or so. We also see sometimes pure amplitude modulation, sometimes pure phase modulation, sometimes a mix of both. It also seems to depend on the location, and hence on the metallicity, maybe, whether you have more or less Blaschko effect. It seems that stars that have very long periods, at that time, there were very few known that had a Blaschko effect, so these were troubles for these models. So they were insufficient, and that's why Stotters came up with this new model in which you don't need a non-radial mode. You can just remain with the Lyrae star, and in the Lyrae star, which has a specific stellar structure, and you have in the outer layers turbulent convection. And in Stotters' model, there's a magnetic field that is variable in strength, and that would give a variable turbulent convection, and that is what will influence the amplitudes of the pulsations. So he proposed it in 2006, but he referred to previous papers saying this is actually an old idea. So from 2006 to 2010, this new model suddenly came on the scene, and it was proposed as a new possibility to explain the Blaschko effect. Now, in the meantime, we had been observing light curves, we had been doing frequency analysis, we had seen that for non-modulated stars, you have this very nice main mode, and then it's harmonics, because it's a very peaked variation. But if you have an Lyrae star that's modulated, you would see in this frequency spectrum multiplets, doublets, triplets, quintuplets, and even higher order multiplets, even more side peaks. If you look in a lot of detail, and especially with the space data now we can do that, you will see that sometimes you see a lot of components there. And the models didn't really predict that. So photometry already indicated that something else is going on maybe, or something more. And then at the same time, if you look at the spectrum of a star, you can get much more information of what is happening in depth in different layers. And there were early studies in the 50s and the 60s of Lyrae looking at spectra of the star and combining these spectra with photometry, and we would see that in certain phases there are shock waves going through the star's atmosphere. Here you see at this phase in the rising branch, if you look at what's happening in velocity, if you look at radial velocities from spectra, you see that there are shock waves here. You can see this also in the U minus B, so there's an increase. You'll see some emission in the Balmer lines sometimes in specific phases in this pulsation cycle of Lyrae. And what this shows is that these Lyrae stars, they have very tumultuous atmospheres, and so they might seem to be behaving very, very quietly and repetitively, but as several authors already demonstrated, actually the atmospheres are very turbulent, very tumultuous, and you need nonlinear pulsation codes to describe it. You have this effect of variable speeds of the layers at different depths. 10 minutes? Okay, thank you. And so we see that looking at different lines, actually you get different behavior of the line. So you see that at different depths in the star, you get different behavior. So what this shows is that you could actually go and look at these spectra to figure out what exactly is happening in these stars. And that next to all the data that we had been gathering, specific data also from micro-lensing surveys, from satellite missions, you could also look at the spectra. Now, in the meantime, when we had these three models, we also were lucky to have Kepler up in the sky, and Robert already talked about the space revolution for variable stars. Now, for our Lyrae stars, this was also a revolution. And we have this working group on Kepler data, on TESS data, that is focusing on data analysis, but also on modeling what we see, and then also in collaboration with several of you, the ground-based follow-up for the stars that are observed in detail by the satellites. Now here you see some Kepler data of our Lyrae stars. You see the two cadences. This is one data point every 30 minutes. This is one data point every minute. And you see that to study these phases where there are shock waves in the star, these data are super useful because you can see really tiny changes very well. Now, the revolution for our Lyrae stars was by looking just simply at the photometry. And when we got the first data for our Lyrae stars with Kepler, we saw some stars that were completely clockwork, very, very repetitive, no changes. And then we saw stars that were modulated. This is a star that showed no changes at all, even when we looked at this less than millimagnitude level. But then here, from the first batch of data, you see that some are very modulated. So the variation is very short, and you see this envelope for different Blasco star, a whole zoo. Of course, yeah, it requires some stitching together to get to this variation, but you see Blasco effect is not repetitive, but for some it is. And then, by a very fortunate coincidence, our Lyrae itself was in the field of the Kepler data. So here you see it. We knew it was in the constellation of Lyra, and Kepler was looking on in this part of the sky. But we knew also it's too bright for Kepler. Actually, it will completely saturate the CCD, which it did, as you see here. But then when we got the first data, we saw a star that was having the same period as our Lyrae. It was our Lyrae itself. And we saw some interesting effects, but we didn't know whether we could trust it because the data on the CCD looked like this. So we went back to talk to the people at NASA who did the reduction, and we asked them, could you maybe help us to really reconstruct from this saturated signal the exact light curve? And Steve Bryson, who became a friend through this whole process, he devoted a lot of time trying to reconstruct the light curve from what it was initially, this blue striped line, to what our Lyrae was doing in reality. And so our Lyrae actually became a prototype not only of the class, but also of stars that are too bright in the field to make reconstructions of the photometry. And so this is the first star for which they did it. Later they did it for other stars. And after doing this, we got this very nice light curve just for free after a bit more than a month of observations, and here another few months. And I compared this with the data that I got painstakingly about 5 years before, working with different observatories, spending more than 2 years to stitch them all together. And you see the kind of changes that this brings in the frequency spectrum. Here you have data from 7 observatories. Of course, you have the one-day aliasing because they are observed from the ground. And here you have this very clean spectrum because it's all taken from space with one single telescope. And of course, if you have this, then you can start to see a lot of extra things because all the grass here that is just noise is taken away. And let's zoom into this because actually this is our Lyrae. This Blasco modulated star is our Lyrae. And if we zoom into this part, then we can see that you have alternatingly higher and lower maxima in this star. And this is something that we had never seen from the ground. If you do a frequency analysis, because you have up and down effect, you have a double period here. Up, down, that's a double period. So that means in the frequency spectrum, you will see half the frequency. And that's what we see here. So these are the half integer frequencies. Robert did a study over multiple quarters of our Lyrae, and this is just from the second quarter, but later it was done for more. And you see that this period doubling effect, as we call it, it is observed not always to the same extent. So here you see it for 3 parts in the rising branch of the Blasco cycle, and you see that sometimes it's strong, sometimes it's less strong, as you see here. So it's a bit chaotic. Now, when we saw it and we talked about it with colleagues, it was reminiscent of effects that we see in Cepheids, where a resonance between different radial modes would cause this kind of behavior, of this up and down, and that's why it was never seen in our Lyrae stars. It was never even predicted, but it had been predicted for Cepheids, and we had people in our group that had done these models, and they said, yeah, let's do the models again. And it turned out that a similar resonance as would cause period doubling in Cepheids would work for our Lyraes, and there could be a resonance between these fundamental modes and a higher order radial modes, the 9th overtone, they think, so with a lot of notes in between, and that this could cause this up and down effect. Now, because this resonance was only seen in this period doubling, we saw it in our Lyrae, but afterwards we saw it also in other Blaschko stars, a link was made between the period doubling and the Blaschko effect. And this led to a new model that said that what causes the period doubling could also cause the Blaschko effect. Now, interestingly, this effect is quite strong, this period doubling. Sometimes it's really like it's almost a 10th of a magnitude sometimes, between 2 consecutive cycles. So that's big. Why was it never seen before? Well, it's because we were observing from Earth, usually from one side, and our Lyrae stars have periods of half a day, so you would typically miss the next cycle, and then you would not see it. But yeah, we now saw it thanks to space data, and it led to a whole batch of new models, and it led to this radial resonance model that I just described. And since then, we have this condition. Now, I have 5 minutes left, so I'll just go quickly through maybe scrapping some of the models. This variable turbulent model, we used the Kepler data to see whether it could work, so whether because colleagues had tested it on ground-based data. We also did the same for the Kepler data. And we saw that basically it's quite hard to get this big change in the turbulence to cause such a big variation on several scales of several days. Now, we looked, of course, at many more stars than our Lyrae, and we found a lot of things. So we found stars that pulsate in the 2nd overtone. We found very interesting RRC stars, and I could talk a whole hour about just these stars, because I think the RRC stars right now are maybe the more interesting ones, because they show very interesting period ratios that could only be due to non-radial modes. We have some crazy stars that sometimes seem to behave like an RRAB, sometimes like an RRC. And for all of these stars, we also got spectra to really get their parameters more precise. So that's all the things that we did. Now, to make the story round, we started with the data from Williamina Fleming in 1913. And then 1 century later, we had this Kepler data, much denser, of course, entering a new era. But entering this new era, with all the extra things that we see in our Lyrae stars, we have a lot of additional questions, of course, and we want to know, okay, how are these behaviors that we see linked with the physical parameters of the stars? Is there an effect on distance determination, because we use these stars as tools? And yeah, there's a lot to be said about the more recent studies done also on the test data, but the bottom line is that we see much more than we have seen from the ground before. Yet, I want to return to the ground, because most of us are mostly using ground-based telescopes. And what can we do from the ground? Not X-ray data, but we can do a lot of other things. We can use small telescopes to look at our Lyrae stars. And that we can even use tiny telescopes. So that was what brings me to the paper of Jean-Francois and colleagues, in which our Lyrae, even beyond the Kepler campaign, was followed, and it's still being followed, I think, every night or whenever it is up, right? Then to see what is happening. And what we had seen in the Kepler data, namely that the Blaschko effect was diminishing, was decreasing during the Kepler campaign, was confirmed by data from the very tiny telescope that is operated by Jean-Francois and colleagues. And it's very important to follow these stars over longer timescales and to see what is happening there. That's a very, very important research that has to be continued. And of course, space data cannot give this because they'll give occasional data of the auroral Lyrae stars. Of course, you could also see, okay, what we see in this frequency spectra, how can we model it? And this is an interesting study by Josef Benke from Konkoly Observatory to see how can what we actually see in the frequency spectra be explained if we look at auroral Lyrae stars as modulated signals. Very interesting to look at if you're interested in the details of the frequency spectra. And then, of course, I always want to come back to the spectra because I know that there's a lot of truth in there, but it is challenging to be done. And this is very early data, again, from Preston and collaborators. These are data that we got over different cycles, over one Blaschko phase and other Blaschko phases. And of course, if you have spectra and you can see, these are data from my thesis, what the spectral lines do over longer time ranges, then you can really get back to what is happening inside the star. And these are models by André Fokine of what is happening inside the star as the star changes brightness. Actually, you have different layers that are colliding with each other. And this is something that your spectroscopy might give you more insight in. This is from my thesis. What you see on the left is a star that is purely radial. And what you see is one spectral line. And as the star expands and contracts, you will see, because of this pulsation, a Doppler effect on the line. And you will see this line move back and forth if you have time series spectra. Now, if you add a small non-radial mode to the star, a tiny one, you will see how this changes the shape of the line. And so to really do mode identification, you could also use spectra. That's what I try to do here. You see it for a more complex mode, and you see how much different pulsation modes will influence. Okay, and to end with, this is a study done by my PhD student, Salma Silla, based on data that were obtained by some of you. And this is no O-C diagram of an auroral Lyrae star that is suspected to be in a binary system. Because as I said in the beginning, we don't know many auroral Lyrae stars that are in binaries, which is a pity. But many of them should be in binaries, just not detected. And what we did here is we got the data from GEOS, but what we tried to do is to reduce the scatter by really fitting this Blaschko effect very precisely. And so this is a paper that we're preparing that will be submitted very soon, in which we want to extract the Blaschko effect in order to get a much better determination. And I look forward to exchanging with some of you who have gotten data. I think, Mr. Fumagalli, you have also gotten data of some of the stars we've looked at. And it's very, very, very good for us that we have these complete light curves of the stars, because that can allow us to really extract a Blaschko effect much better, because it is an effect that will disturb what we want to identify as an orbit. And with this, we end. And as you know, we have these meetings on our Lyrae stars and Cepheids, to which you are warmly welcome. We've met in several of these meetings, but this is where we discuss all this kind of stuff during a week. Thank you.
Thank you, Katrien, for this very elaborated and a lot of data and a lot of information talk about auroral Lyrae stars, only auroral Lyrae stars. So you can imagine if you add other types, what information is available nowadays. So I open the talk for questions or comments, please.
I will break the ice. Usually when we observe the whole curves of Lyrae at the very beginning, before it reaches the maximum, at the minimum, we see many variations. It's like a mess. We don't really see a nice, you see a nice curve. What is it due? Is there something
yeah.
special happening there. Thank
You
you.
mean at the minimum light, and then around maximum light you see a mess? That it's the photometry is more in the minimum. Yeah, near the minimum. Yeah, so near the minimum you have the so-called bump phase as well. So which is also a shock wave going through the star. Because you have it could be a reflected shock as well. So if we go back to the models by Fokine, you see that in different phases of the star, this one, sorry. Yeah, basically, in different phases of your pulsation, you will have layers in the star that are colliding with each other, that at the surface of the star will give a different total light output. And so you see this on the rising branch, but there we sometimes have this hump phase, which is, if you look in spectra, that's when you should see a shock wave. And then if you go down to the lower part of the light curve here, you often have this hump phase. And that's also, actually, if you look at spectra there you also have a shock wave. And in the models, you will also observe this shock wave. So you have different layers colliding with each other. And this is when the star goes to, here it's close to minimum radius. You see here how it correlates with the radius. And you see that in some phases you have layers colliding with each other. And that's what gives this scatter closer to minimum light. Yeah. And yeah, depending on the star, it might be stronger or less strong. And if it's a Blaschko star, this bump will also change position. One of my students did his thesis on this, the changing bump, because it might give also clues to what is exactly happening, because it changes over the Blaschko cycle. So these shocks sometimes come earlier and sometimes later. Yeah, and are sometimes stronger and sometimes less. Yeah. Yeah, there's a lot to uncover still. And simple data like photometry can already give a lot of information, which you can then try to unravel. Yeah. Thank you.
One last question.
Yeah.
One last question.
So you said you made a page with Salma Silla, and you said you had to fit something very precisely. What happens if you don't fit it very precisely?
Thank you. That's a good question. So yeah, that's a good question. Basically, this is how the time of maximum changes for the star, and you see that it's varying a lot. And what we do is we fit what the star does, and this is what the star does, so we have these data, and we try to fit it very precisely, and we use this red curve, which is much better than what is normally done for the O-C. Normally you just use one period, which is the blue curve, and you see if you fit it better, and that's what's shown in this figure, if you fit it better, then you will get much closer to what the star is actually doing. And then you can take out the Blaschko effect, which is the star itself, and you remain with what the orbit is doing, the light time effect.
Thank you.
Thank you.
Okay, so we thank the speaker again.